The closest star to our Sun has a name. Alpha Centauri. Say it slowly, and it sounds almost gentle, like something written on an old map, or whispered in a planetarium while the lights go down. But here is what that gentle name contains. If you left for it tonight, your great-great-great-grandchildren would not live to see it arrive. That is not a metaphor. That is where we actually live. Get comfortable now. Let your shoulders drop. Let the day finish its slow release. Tonight, we are going to travel to the nearest star together. Not quickly, not with fear, but with honesty and with wonder. Because the journey to Alpha Centauri is not just a story about distance. It is a story about what it means to be a small, warm, briefly living thing in a universe that is almost incomprehensibly large. You do not need to remember anything tonight. Just listen. Just breathe. We go slowly, and we go together. There is a particular kind of comfort in the night sky that most people never fully examine. On a clear evening, far from city light, the stars feel close. Not close in a way you could measure on a map. Close the way a candle across a dark room feels close. Present. Reachable. Part of the same world you are standing in. That feeling is one of the most beautiful illusions the universe offers. The stars are not close, not even the nearest ones. And understanding just how far away they actually are, really sitting with that distance, not as a number on a page, but as something you can feel in your chest, is one of those experiences that quietly changes the way you see everything else. So let us begin there. With the star next door, Alpha Centauri is the closest stellar system to our Sun. If you live in the southern hemisphere or near the equator, you can see it on a clear night with your naked eye. It appears as a single bright point, one of the brightest in the entire sky, sitting in the constellation Centaurus. For thousands of years, sailors used it to navigate. Ancient peoples of the southern lands watched it rise and set with the same quiet reliability as the moon. In every practical sense, it is our nearest neighbor among the stars. But the word neighbor carries a warmth the reality does not quite support. When we say Alpha Centauri is our nearest neighbor, what we mean is this. The light you see leaving that star tonight will take 4 years and roughly 4 months to reach your eyes. Not 4 years traveling from some distant corner of the galaxy. 4 years just to cross the gap between us and the closest thing to our Sun that exists anywhere in the universe. 4 years. Just to get here. That might not sound immediately staggering. We measure things in years all the time. A 4-year degree. A 4-year election cycle. 4 years feels like something a human life can hold without difficulty. But we are not talking about waiting 4 years. We are talking about light itself making that journey. And light does not slow down. It does not stop for anything. Light travels at approximately 186,000 miles per second. In a single second, it circles the entire Earth 7.5 times. In 8 minutes, it crosses the 93 million miles between our Sun and our planet. In 4 years and 4 months, moving at that speed without pause, it crossed the distance to Alpha Centauri. That distance has a name, 4.37 light-years, and that number, sitting quietly in a sentence like any other measurement, is one of the most humbling figures in all of science. Now, large numbers have a problem that nobody talks about enough. We treat them as if understanding them is simply a matter of reading them correctly, as if the moment a number appears on a page, the mind absorbs its true meaning. But that is not how human comprehension works. Our brains are remarkably good at feeling the difference between one apple and 3 apples, reasonably good at imagining a room with 10 people versus a room with 100. But somewhere around 1,000, something starts to slip. The numbers keep climbing. The felt sense of scale stops climbing with them. 1,000,000 and 1,000,000,000 sound similar when you say them out loud. They are not similar. They are 1,000 times apart. So instead of asking you to hold 25.6 trillion miles in your mind, which no human being can genuinely do, let us try something different. Let us shrink the universe until the feeling fits. Imagine the sun is an orange, a bright, ordinary orange, about 4 inches across, sitting on a kitchen table somewhere in New York City. On that scale, where is Earth? Earth is a grain of sand, not a marble, not a pea, a single grain of sand, circling the orange from about 35 feet away, just past the kitchen door. Hold that image for a moment, because it is already remarkable. Your whole world, every person you have ever loved, every road you have ever driven, every city, every ocean, every memory you have ever made, all of it riding a grain of sand, 1 room away from a piece of fruit. Now ask yourself, on that same scale, where is the next orange? Where is Alpha Centauri, the nearest star to our sun? Take a guess before I tell you. Down the street, across the park, on that scale, the nearest star sits approximately 2,700 miles away. Not 2,700 feet, not 2,700 blocks, 2,700 miles. If our orange sun rests on a table in New York, the nearest other star sits somewhere past Los Angeles, and between them, in this shrunken model where your entire world is a grain of sand, there is essentially nothing at all. A few drifting atoms. Emptiness so complete it barely has a name. You could travel from the orange in New York to the orange near Los Angeles, the entire breadth of a continent, and never once strike anything larger than a speck. That is the emptiness between stars. That is what 4.37 light-years actually means, when you press it into a shape the mind can hold. Now there is something else worth knowing about Alpha Centauri, something that adds a layer of beauty to its already remarkable nature. When you look at that point of light in the southern sky, you are not looking at one star. You are looking at what appears to be one, but is in fact a system of 3. The 2 brightest members are called Alpha Centauri A and Alpha Centauri B. They are remarkably similar to our own Sun. Alpha Centauri A is slightly larger and brighter, roughly 1.5 times more luminous. Alpha Centauri B is slightly smaller and dimmer, about half as bright. Both are sun-like stars, the kind astronomers consider promising candidates when thinking about where life might exist elsewhere in the universe. These 2 stars orbit each other, not the way a planet orbits a star. Both move. Both affect each other's path, locked in a gravitational partnership that has persisted for billions of years. Their orbit around their shared center takes approximately 79 years to complete. At their closest, they come within about 11 astronomical units of each other, roughly the distance from our Sun to Saturn. At their farthest, they drift to about 36 astronomical units apart. The third member of the system holds the title of closest star to Earth. Its name is Proxima Centauri. Proxima is a very different kind of star, a red dwarf, small, dim, and cool by stellar standards. It glows a deep reddish orange rather than the warm yellow-white of our Sun. At only about 1/8 the mass of our Sun, it burns its fuel so slowly that it is expected to live for approximately 4 trillion years, roughly 300 times the current age of the universe. In stellar terms, Proxima Centauri is barely getting started. Proxima orbits Alpha Centauri A and B at an enormous distance, so far out that some astronomers debate whether it is truly gravitationally bound to the other two, or simply a very close neighbor passing slowly through. At its current position, Proxima sits about 4.24 light-years from Earth, making it fractionally closer than A and B. That fractional difference is what earns it the name Proxima, from the Latin for nearest, and Proxima Centauri has something else. In 2016, astronomers announced the discovery of a planet orbiting it, a world roughly the size of Earth, sitting within the zone where liquid water could theoretically exist on its surface. They named it Proxima Centauri b. We will return to that world later in our journey. What astronomers have learned about it since its discovery is one of the more surprising and quietly sobering chapters in this story. For now, simply hold this image. 3 stars, bound together across the void, 2 of them sun-like, warm and stable, circling each other in a slow cosmic waltz that has been turning since before our own sun existed. One of them small and ancient and patient beyond imagination, with a world nearby that might, in some configuration we do not yet fully understand, have conditions that matter to life, and all of it sitting on an orange 2,700 miles from yours. There is something both humbling and strangely comforting in that image. Once you let it settle, the universe arranged these lights in the sky according to rules that have been running since before our sun was born. The fact that we can see Alpha Centauri with our naked eyes, that it has guided sailors and sparked the curiosity of astronomers for centuries, that it sits close enough for us to study in detail, but far enough to remain genuinely mysterious. That feels, in its own quiet way, like a particular kind of gift, a gift we have not yet found a way to reach. But before we can talk about reaching it, we need to understand exactly how far that orange really is, because the scale model gives us the shape of the emptiness. What it does not yet give us is the feel of it in time, in years, in the only currency human lives actually run on. So let us add one more layer to the picture. Not miles this time. Time. Light crosses the distance from Earth to the Moon in about 1.3 seconds. It crosses from Earth to the Sun in 8 minutes. It crosses from the Sun to Neptune, the farthest major planet, in roughly 4 hours. And it takes 4 years and 4 months to reach Alpha Centauri. 1.3 seconds, 8 minutes, 4 hours, 4 years. Read that progression again slowly. 1.3 seconds, 8 minutes, 4 hours, 4 years. The jump from 4 hours to 4 years is not a gradual increase. It is not the next step on a smooth curve. It is a wall, a cliff in the scale of things. The entire span of our solar system, from the Sun to the farthest planet, takes light 4 hours to cross. and then 4 years of additional travel just to reach the nearest neighbor. That cliff is where our solar system ends and interstellar space begins. And it is the cliff that every idea about reaching Alpha Centauri has to somehow get past. Now, when someone proposes a spacecraft traveling at 10% of the speed of light, which would be an almost unimaginable technological achievement far beyond anything we have ever built, the journey to Alpha Centauri would still take approximately 43 years. 43 years at 10% of the speed of light. When someone proposes 20% of the speed of light, the most optimistic target of the most ambitious interstellar project currently being seriously discussed, the journey shortens to about 21 years. 21 years of travel, one way, to the nearest star, and both of those speeds are not things we currently know how to achieve for any object larger than a very small probe. To understand why, we need to know exactly where we are starting from, not where we hope to be, where we actually are right now, the fastest things our species has ever built, the records we have actually set, the speeds we have genuinely reached. That is the next chapter. And the numbers, when laid honestly against the distance to Alpha Centauri, will clarify everything that follows. Human beings have been building things designed to move for as long as there have been human beings. First we walked, then we ran. We built rafts and learned that water could carry us farther than our legs. We built boats for rivers, then coastlines, then oceans. We built engines. We built aircraft that left the ground entirely. And then, in the middle of the 20th century, we built something that could leave the planet. That last achievement still carries a particular weight. There is a reason the launch of Sputnik in 1957 and the first human spaceflight by Yuri Gagarin in April of 1961 are remembered as turning points, not just in technology, but in what it means to be human. We had spent our entire existence as a species on the surface of one world. Then, in the span of a single generation, we learned to leave it. The question tonight is a natural extension of that achievement. We left the planet. Can we leave the solar system? Can we reach Alpha Centauri? To answer honestly, we need an honest inventory, not the ships of science fiction, not the warp drives and hyperjumps of stories we love. The actual ships, the ones we have built, launched, and tracked across the decades as they traveled away from Earth. What is the fastest thing our species has ever created? The Saturn V rocket, the most powerful launch vehicle ever successfully operated, generated more than 7.5 million pounds of thrust at launch. Its actual speed in space, coasting toward the Moon after escaping Earth's gravity, was roughly 24,000 miles per hour. 24,000 miles per hour. That is extraordinary by the standards of anything on Earth's surface. Commercial aircraft fly at 500 or 600 miles per hour. A car on a highway does 70 or 80. 24,000 is about 40 times faster than a commercial jet. Fast enough to circle Earth in a little over an hour. Now, can you guess what journey time that gives us to Alpha Centauri? At 24,000 miles per hour, the journey would take approximately 114,000 years. 114,000 years. Not 114. Not 11400. 114,000. Let us find something faster. The Voyager probes. launched in 1977 to study the outer planets, received additional boosts from the gravitational pull of Jupiter and Saturn as they flew past. This gravitational assist technique uses a planet's gravity to accelerate a spacecraft without additional fuel. An elegant piece of physics. Voyager 1, currently the most distant human-made object in existence, travels at approximately 38,000 miles per hour relative to the Sun. At that speed, the journey to Alpha Centauri would take approximately 73,000 years, longer than recorded civilization, longer than agriculture itself. Every human society that has ever grown a crop, built a city, and written down its history would fit inside a fraction of that journey. Let us keep going. The Helios probes, launched in the 1970s as a joint mission between the United States and West Germany, were designed to study the Sun. By falling deep into the Sun's gravity and accelerating around it, the Helios 2 probe reached speeds of approximately 157,000 miles per hour at its closest solar approach, 4 times faster than Voyager 1. At that speed, a journey to Alpha Centauri would take approximately 18,000 years. Still thousands of years. Then came the current record holder, the Parker Solar Probe, launched in 2018, was designed specifically to fly closer to the Sun than any spacecraft before it. During its closest passes, it reaches speeds of approximately 430,000 miles per hour. As its mission continues and it makes additional close approaches, that speed is expected to increase further. At 430,000 miles per hour, a journey to Alpha Centauri would take approximately 6,600 years. 6,600 years. We have come from 114,000 down to 6,600. That is genuine, meaningful progress. The kind that, if you squint optimistically, represents a real trajectory of improvement. But 6,600 years is longer than the span from ancient Mesopotamia to right now. Every generation born since the first cities rose along the Tigris and Euphrates could have lived and died, followed by dozens more generations, and the spacecraft would still be traveling. And there is something important to understand about the Parker Solar Probe's record speed. It achieves those peak numbers only during its closest solar approaches. Using the Sun's gravity as a slingshot, it cannot be pointed at Alpha Centauri and simply launched at 430,000 miles per hour on a straight outbound trajectory. The physics of how it achieves that velocity are specific to its orbit around the Sun. Replicating those conditions for a journey to another star is a fundamentally different and far more complex engineering challenge. So here is the honest picture this inventory gives us. The fastest things we have ever built, using every trick available, including gravitational assists and extreme solar orbits, achieve speeds that are roughly 1,000th of 1% of the speed of light. And at those speeds, interstellar travel is not measured in years or decades, but in thousands to hundreds of thousands of years. This is not a pessimistic observation. It is the starting line. The history of human technology is a history of crossing gaps that once seemed uncrossable. Walking to sailing, sailing to flying, flying to orbit. Each transition required not just better engineering, but a fundamental shift in approach. New principles, new energy sources, new ways of thinking about what was possible. The gap between our current fastest spacecraft and the speeds needed for practical interstellar travel is real. It is large, but it is a defined gap. And human beings have a particular talent for looking at defined gaps and spending generations figuring out how to close them. What stands between us and Alpha Centauri is not a mystery. It is physics, and physics, unlike many things in this universe, is at least willing to be understood. But first, we need to understand exactly what that physics demands. Because the numbers we have just reviewed are not simply the result of our engines not being powerful enough, there is a deeper problem built into the very nature of how we move things through space. A problem described mathematically more than a century ago. A problem that has not gone away since. It is called the rocket equation, and it is one of the most quietly devastating constraints in all of engineering. There is a particular kind of problem in science and engineering that looks, at first glance, like a temporary obstacle, something that exists because we have not yet been clever enough to solve it, something that will eventually yield to better materials, better designs, better minds, working on it over a longer period of time. And then there is a different kind of problem, one that does not yield to cleverness or resources or time. Not because the effort is insufficient, but because the problem is built into the fundamental structure of how the universe operates, a wall made not of ignorance, but of mathematics. Mathematics does not retreat when you push against it. The rocket equation is the second kind of problem. It was described formally in 1903 by a Russian schoolteacher and visionary named Konstantin Tsiolkovsky, a quiet, largely self-educated man who spent his evenings in a small wooden house in the provincial city of Kaluga, working through the mathematics of space travel decades before anyone had built anything capable of leaving the atmosphere. Tsiolkovsky never saw a rocket launch. He never worked at a government laboratory or a prestigious university. He was a rural teacher who published his work in small scientific journals that few people read at the time. But his equation was correct. It remains correct today. And it contains a constraint on rocket travel that is, once you understand it fully, almost difficult to accept. Here is the core idea, expressed without any mathematics at all. A rocket moves by throwing mass out of its back end. That is all a rocket engine does. It takes propellant, burns it or accelerates it in some way, and ejects it backward at high speed. The reaction to that ejection pushes the rocket forward. Elegant, simple, real. The problem begins when you ask a straightforward question. How do you make a rocket go faster? The obvious answer is to burn more propellant, eject more mass, get more push. This is correct. But here is where the equation reveals its teeth. That additional propellant has mass, and that mass needs to be carried from the very beginning of the journey. Carrying extra mass requires even more propellant to accelerate it. And that extra propellant has mass too. Do you see the trap? Every time you add propellant to go faster, you add mass to the vehicle. Added mass requires more propellant. More propellant adds more mass. The relationship is not linear. It does not scale gracefully. It explodes outward in a way that becomes, at high enough speeds, essentially impossible to satisfy. Let us make this concrete with a real example. The Saturn V rocket stood about 363 feet tall and weighed approximately 6.2 million pounds at launch. The overwhelming majority of that mass was propellant and the structures built to hold and burn it. The actual spacecraft payload sitting on top represented only a small fraction of the total. and the Saturn V was only going to the Moon. A journey of 239,000 miles at relatively modest speeds, nothing close to the velocities required for interstellar travel. Now ask yourself this: what would the rocket equation demand for a journey to Alpha Centauri at 10% of the speed of light? 10% of the speed of light is approximately 67 million miles per hour, about 1,700 times faster than the Parker Solar Probe at its peak. When you apply the rocket equation to that speed requirement using conventional chemical propellant, the required fuel mass reaches into the billions of times the payload mass. Not million, billions. The most energetic chemical reactions we know of simply cannot provide enough energy per kilogram of propellant to make the numbers work. There is no chemical propellant that solves this problem. Not with any amount of engineering ingenuity applied to the chemistry itself. Using chemical rockets to reach Alpha Centauri is roughly like trying to cross the Atlantic Ocean by swimming very efficiently. Swimming is real. The technique is genuine. But the scale mismatch between the technique and the task is so severe that no improvement in swimming will bridge it. The problem is not the swimmer. The problem is the category of solution. This is why serious discussions of interstellar propulsion always move past chemistry. Nuclear energy is roughly 1,000,000 times more energy dense than chemical energy. Nuclear propulsion concepts offer genuine and significant improvement over chemical rockets. They begin to address the scale problem in a meaningful way. But even nuclear propulsion, in the forms currently understood and tested, runs into its own version of the rocket equation's constraints at high interstellar speeds. There is one form of energy that sidesteps the rocket equation more completely than anything else. The most energy-dense process known to physics: matter-antimatter annihilation. When matter and antimatter meet, they do not burn in the chemical sense. They annihilate each other completely, converting 100% of their combined mass directly into pure energy. This is the most efficient energy release physically possible. A matter-antimatter drive, in theory, could reach a significant fraction of the speed of light with fuel mass ratios that are at least not completely absurd by comparison to everything else we have discussed. There is one small difficulty. Antimatter is extraordinarily difficult and expensive to produce. The total amount of antimatter ever created by human technology across every particle accelerator ever built in all the decades of high-energy physics research would not be enough to power a flashlight for more than a fraction of a second. Producing the quantities required for an interstellar mission would require energy inputs and infrastructure separated from current human capability, not by years of engineering effort, but by centuries. At minimum, not impossible. Nothing about matter-antimatter annihilation violates any known physical law. But not soon. So here is where the rocket equation leaves us. Chemical propulsion cannot get us to Alpha Centauri on any timescale relevant to human civilization. Nuclear propulsion offers genuine improvement, but faces severe limitations at interstellar speeds. Antimatter propulsion would theoretically work, but requires technology we are nowhere near possessing. This is an honest map of the territory. And maps, even maps that show difficult terrain, are more useful than maps that lie about what is there. There is one more thing worth understanding before we move on. The rocket equation does not just constrain how fast we can go, it interacts with everything we need to bring along for a journey of decades. Food, water, air, spare parts, medical equipment. The mass of a life support system capable of sustaining human beings for decades, is itself enormous. And every kilogram of life support added to the spacecraft needs to be accelerated, which requires more propellant, which adds more mass, which requires more propellant. The equation compounds. It does not forgive. It does not care how clever the engineering is. What this means in practical terms is that the question of getting to Alpha Centauri is not simply a question of building a bigger engine. It is a question of rethinking, from the ground up, almost everything about how we move through space. That rethinking is happening, slowly, carefully, with the kind of patient ambition that serious science requires. But first, there is another obstacle to understand. One the rocket equation cannot even see, because it lives not in the machinery of the spacecraft, but in the bodies of the people inside it. The human body. It turns out the universe has very specific opinions about what flesh and bone can survive across years of deep space, and those opinions are worth sitting with before we go any further. Close your eyes for a moment and imagine you are floating. Not the gentle floating of a swimming pool, the absolute floating of a spacecraft in deep space. No floor pressing against your feet, no chair supporting your back, no sense of up or down at all. Your coffee, if you had any, would drift in a wobbling sphere in front of you. Your arms would hang without weight, curving slowly in whatever direction they last moved. It sounds peaceful, and for a few hours, or a few days, it probably is. But here is a question worth asking before you get too comfortable with that image. How long do you think the human body can enjoy that weightlessness before something starts to go wrong? The answer, as space medicine researchers have documented through decades of real data gathered from real people on real missions, is that the body begins responding much sooner than most people expect. Because the human body was not designed for this, it was shaped by 3.8 billion years of evolution on a world with a surface, with gravity, with constant downward pull that bones and muscles and hearts and eyes have been calibrated to resist every moment of every day since long before our species had a name. Remove that pull, and the body begins to respond. Not always dramatically, not always immediately, but persistently, in ways that compound with a thoroughness that is difficult to reverse. Let us begin with the simplest thing. Muscle. Your muscles do not just move you. They resist gravity constantly, even when you are standing still, even when you are sleeping. That low-level, continuous resistance is what keeps them strong. Without it, muscles shrink faster than you might expect. Astronauts aboard the International Space Station exercise for approximately 2 hours every single day. Not for fitness, not as a preference, because without that 2 hours of specifically designed exercise, muscle loss would become severe enough to compromise their ability to function by the end of a 6-month mission. 2 hours a day, every day, for 6 months. Now imagine a journey to Alpha Centauri lasting 20 years. What exercise equipment maintains its function for 20 years of daily use in a spacecraft environment, where a repair technician cannot simply be called? What happens the month the treadmill breaks and the replacement part is, conservatively, 20 light-years away? Bones present the same challenge. Bone density, like muscle mass, depends partly on mechanical loading from gravity. In microgravity, bones lose density at a rate roughly 10 times faster than elderly people with osteoporosis on Earth. Exercise and medication slow this, but do not fully prevent it. Then there is the heart. On Earth, one of the heart's jobs is pushing blood upward against gravity from your lower body toward your brain. In microgravity, that job disappears. The heart adapts. It becomes slightly smaller, slightly less efficient at the pumping work it will need to do again if the traveler ever returns to gravity. Blood redistributes toward the upper body and head. Astronauts describe a persistent sensation, not unlike hanging upside down, their faces puffy, their sinuses congested, and their vision, in some cases, permanently affected. A condition called spaceflight-associated neuroocular syndrome has been documented in a significant percentage of astronauts who spent 6 months or more in space. It involves structural changes to the eye and the optic nerve that can result in lasting vision impairment. The leading hypothesis involves shifts in cerebrospinal fluid pressure in the absence of gravity, for a mission lasting not 6 months, but years or decades. The implications for crew vision are serious and currently unresolved. Now let us talk about radiation. On Earth, 2 things protect you from the most energetic particles in space: the planet's magnetic field, which deflects charged particles before they reach the surface, and the atmosphere, a column of air that absorbs and scatters whatever gets through. In deep space, neither protection exists. The 2 primary radiation sources are galactic cosmic rays, high-energy particles accelerated to enormous speeds by supernovae and other violent astronomical events throughout the galaxy, arriving continuously from all directions without pause, and solar particle events, sudden bursts of radiation from solar flares that can deliver very high doses over short periods. For a multi-year mission beyond Earth's magnetic field, cumulative radiation exposure becomes one of the most serious health constraints of the entire enterprise. Heavy shielding reduces the dose but adds mass, which feeds back into the rocket equation. There is no clean solution, only management. And then there is the challenge that receives the least attention in technical literature, but may be the most fundamentally human of all: psychology. The psychological effects of long-duration spaceflight in isolation have been studied both through actual missions and through analog studies on Earth, extended stays at Antarctic research stations, submarine deployments, dedicated isolation experiments like the Mars 500 study, which confined 6 volunteers to a simulated spacecraft for 520 days in 2010 and 2011. The findings are consistent enough to be treated as predictable rather than speculative. Sleep disturbances are nearly universal. Crew members show predictable patterns of declining morale roughly 3/4 of the way through a mission. Even when everything is going well, by every objective measure, researchers call this the third quarter phenomenon. It shows up with remarkable consistency across very different missions and very different people. For a journey lasting not 500 days but perhaps 20 years or more, the psychological architecture of the mission would need to be, in some sense, a culture, a set of rhythms and meanings and agreements maintained not for months but for decades, across relationships that would outlast most marriages and most careers. Is that possible? Nothing in the science says it is impossible. Human beings have shown remarkable capacity for enduring difficult conditions when the sense of purpose is strong enough. The crews of long sea voyages, the inhabitants of isolated polar stations, the monastic communities that sustained themselves in constrained environments for generations, but it requires design, intentional, evidence-based design, not just of the spacecraft's physical systems, but of its social ones, its rituals, its governance, the ways that conflict will be resolved and meaning will be renewed across years of travel toward a destination that never appears to grow perceptibly closer. So let us take stock. A distance that requires either speeds we cannot yet achieve or timescales that exceed human lifespans. A propulsion constraint that means achieving those speeds requires energy sources beyond current capability. And now, a biological constraint showing that even if the propulsion were solved, placing human beings inside a spacecraft for the duration would require solving cascading medical, physiological, and psychological challenges that we are only beginning to understand. Each problem is real. Each is well documented. None of them result from insufficient effort by the people working on them. But notice something. Each problem is also specific, defined, researchable. They are walls made of known materials, and walls made of known materials can, at least in principle, be mapped. And walls that can be mapped can sometimes be gone around entirely. Because there is one approach to the problem of human biological limits on a multi-decade journey that does not try to make the body more resilient. It tries instead to make the body less present, to slow it down, to quiet it, to put it, in some meaningful sense, to sleep. There is something almost poetic about arriving here. A video designed to help you fall asleep. Now at a chapter about sleeping through the stars. Not metaphorically, not as a figure of speech, but as a genuine, seriously considered scientific proposal for how human beings might survive a journey lasting decades without aging through most of it. Without losing muscle and bone across 40 years of waking consciousness, without the psychological deterioration that comes from decades of confinement in a metal vessel moving through absolute darkness. The idea is called hibernation, or torpor, or cryosleep, depending on who is discussing it. The names carry different connotations. But the core question is the same. Can we make a human being go dormant? Not dead, not frozen into glass tubes like specimens in a laboratory, something closer to what certain mammals do every winter. A deep, sustained reduction in metabolic activity, a slowing of the body's processes to a fraction of their normal rate, a state in which the biological clock, in some meaningful sense, ticks more slowly. If that were possible, the implications for interstellar travel would be profound. A crew spending most of a 20-year journey in deep metabolic suppression would age far less than a crew spending those years fully awake. Their caloric requirements would drop dramatically, reducing the food to be carried, and therefore the mass of the spacecraft. Their psychological exposure to the isolation of deep space would compress into the periods when they were awake and active. The dream is real. The question is whether the biology is willing to cooperate. Let us start with what we actually know. Hibernation is not rare or exotic. It is widespread in the animal kingdom. Bears, groundhogs, hedgehogs, bats, certain species of lemurs. Many mammals enter states of reduced metabolic activity during winter months. Some of these states are quite profound. The Arctic ground squirrel, for example, reduces its body temperature to just below freezing during hibernation, dropping its heart rate from roughly 200 beats per minute to about 1 beat every few minutes. Its metabolic rate falls to roughly 2% of normal. It sustains this state for months at a time, emerging in spring with muscle mass and organ function largely intact. That last part deserves to sit for a moment. An Arctic ground squirrel does not emerge from months of complete stillness, with the kind of muscle loss and bone deterioration a human being would accumulate from months in bed. Something about the hibernation state protects the body from the degradation that normally accompanies inactivity. The precise mechanisms involve complex hormonal and cellular processes that are still being studied. But they are real. And they work. Humans, unfortunately, are not natural hibernators. We do not have the biological machinery to enter torpor spontaneously. Our metabolic rate does not drop dramatically during sleep. Our body temperature stays within a narrow range. From a metabolic standpoint, human sleep is a modest adjustment, not a transformation. So the question becomes whether we can induce a hibernation-like state artificially, whether medicine can do what evolution did not build into us directly. And here is where the science becomes genuinely interesting, because we already do something related to this. In hospitals, under carefully controlled conditions, for specific medical purposes, therapeutic hypothermia is a procedure in which a patient's body temperature is deliberately lowered, typically to somewhere between 32 and 34 degrees Celsius, to protect the brain and other organs after a severe event such as cardiac arrest or traumatic injury. When the body is cooled in this way, its metabolic demands drop significantly. Cells require less oxygen. The brain becomes less vulnerable to damage from reduced blood flow. Therapeutic hypothermia is not hibernation. Patients require life support throughout. The cooling is modest compared to what a ground squirrel achieves, and it is sustained for hours or days, not weeks or months. But it demonstrates something important. The human body can tolerate significant cooling without permanent damage when managed carefully. The metabolic suppression is real and measurable. Patients recover full function afterward. The gap between therapeutic hypothermia, as currently practiced, and the deep sustained torpor useful for interstellar travel is enormous. Bridging it would require understanding and replicating the molecular mechanisms that protect hibernating animals, solving problems related to how the liver processes toxins at very low metabolic rates, building monitoring systems capable of detecting and responding to medical emergencies in a crew that cannot speak or advocate for itself. None of these problems have been solved. To be completely honest about where the science currently stands, induced human hibernation for durations relevant to interstellar travel remains a theoretical concept. There is serious research happening. John Bradford and colleagues at SpaceWorks Enterprises have published detailed analyses of torpor-inducing transfer habitats for NASA, exploring how pharmaceutical metabolic suppression might be applied to long-duration spaceflight. These are genuine engineering engagements with the concept, not science fiction. But we do not currently know how to put a human being into true hibernation for a year, let alone a decade or 20 years. What we can say, honestly, is this. No known physical law forbids human hibernation. The biology of other mammals demonstrates the general phenomenon is achievable in warm-blooded creatures. The medical precedent of therapeutic hypothermia demonstrates the human body tolerates significant metabolic suppression under controlled conditions, and the motivation to solve this problem, in the context of long-duration spaceflight, is strong enough that serious researchers are actively working on it. Whether that work will eventually produce a technology capable of sustaining human torpor across decades of interstellar travel is a question that belongs to the future. It may take a century. It may take several centuries. It may turn out that certain biological obstacles are harder than they currently appear, but it is not a closed door. There is something worth pausing on here, in the quiet of this chapter. Before we move on, the image of a sleeping crew drifting through the darkness between stars in a state of profound biological stillness carries a particular kind of beauty. The vulnerability of it, the trust required, not in other people, but in the universe itself, in the reliability of physics, in the integrity of the ship, in the hope that the destination will still be there when the eyes finally open. And there is something oddly resonant about it in this moment. As you listen, as your own body begins its nightly practice of letting go, sleep is, in its own quiet way, a form of trust, a surrender of conscious control, a willingness to be carried through a portion of time without being fully present for it. The crew of an interstellar ship, drifting in torpor toward Alpha Centauri, would simply be doing that same thing, across a much larger interval of darkness, trusting the ship, trusting the math, trusting the star to still be there. There is a comfort in that image, if you let yourself feel it. But now we need to consider a harder version of the same question. What if hibernation cannot be solved? What if the biology refuses? What if human beings simply cannot be made to sleep safely through 20 years of interstellar travel? Then the journey does not shorten, and the crew has to live through all of it. Not one crew, perhaps several. There is a thought experiment that arrives quietly and then refuses to leave. It goes like this. Suppose hibernation cannot be solved. Every approach runs into biological obstacles that cannot be overcome with any foreseeable technology. The human body insists on being awake and aging and consuming resources across the full duration of whatever journey you put it on. The dream has not changed. The destination has not moved. Only the constraint has shifted. Instead of finding a way to compress the experienced duration of the journey, you have to find a way to sustain human life across its full length. For a journey of 20 years at optimistic future speeds, one crew could potentially make it. People in their 20s at departure might arrive in their 40s or 50s, changed in ways we cannot fully predict, but alive. For a journey of 40 years, the math gets harder. A crew of 20-year-olds would arrive as 60-year-olds. Assuming health held across 4 decades of deep space exposure, for a journey of 100 years, or 200 years, or the thousands of years current propulsion technology would require. A single crew is simply not the answer. No individual human life is long enough. And so, the concept that emerges, seriously discussed by scientists, philosophers, and engineers for decades, is the generation ship. A spacecraft designed not just to carry a crew, but to sustain a community across multiple human generations. A vessel large enough and self-sufficient enough to be a world unto itself, a place where people are born, live their entire lives, have children, grow old, and die, all within the same hull, moving through the dark between stars. The children born aboard such a ship would never have seen Earth, never felt rain, never stood in open air, never looked up at a sky that extends in all directions without a ceiling. They would know the ship the way we know our planet, completely, naturally, without alternative. And here is the thought that tends to arrive quietly and stay somewhere in some generation of that voyage. A child would be born who would grow old and die without ever being any closer to the destination than they were at birth. Not approaching, not receding, simply in the middle, living an entire human life in the middle of a journey they did not choose and would not see completed. Their whole life. In the middle. What does it mean to be born in the middle of something that vast? The journey would not be something they chose. It would simply be the condition of their existence. Their children would know the same, and their children's children, until, some number of generations later, someone aboard would be the first to know the journey was almost over, that the star their distant ancestors had aimed toward was finally close enough to see growing brighter. The image is one of the most philosophically rich in all of science, and when examined closely, one of the most technically and ethically complex. Let us start with the mathematics of survival. A closed biological community needs to be large enough to remain genetically and socially healthy across many generations. This is not a trivial requirement. A small, founding population carries limited genetic diversity. Over many generations in isolation, certain genetic variants disappear. Rare traits become more common. In extreme cases, recessive genetic disorders become more prevalent as the pool of variation shrinks. Research by Cameron Smith at Portland State University, published in 2014, suggested that a founding population in the range of 10,000 or more individuals would be needed to maintain sufficient genetic diversity across a journey of several centuries, particularly if unforeseen events reduced population along the way. 10,000 people on a spacecraft. 10,000 people require space to live, sleep, and work, air, water, and food. Medical facilities for everything from broken bones to surgery across all age groups. Education for children. Governance for the inevitable disagreements that any community of 10,000 will generate across multiple generations. They require, in short, a civilization. The mass of such a vessel, and the resources required to sustain it across centuries, are staggering by any engineering measure. Some proposals involve cylindrical structures several kilometers in length, potentially rotating to generate artificial gravity through centrifugal force. The engineering is, in principle, possible. No physical law forbids it. But the resources required to build and launch something of that scale dwarf anything our civilization has ever attempted. Now let us turn to the ethical dimension. Because the generation ship raises a question pure engineering cannot answer. Is it ethical to bring children into existence aboard such a vessel? The founders can make a choice. They can weigh the risks and the potential rewards and decide, as adults with full information, that they want to spend their lives on this journey. That choice, however difficult, is at least a choice. The children born aboard the ship did not choose. They cannot choose. The conditions of their existence, the smallness of their world, the destination they will never personally see arriving. All of this determined before they are born, by decisions made by people who will likely be dead before those children are grown. Philosophers who have thought carefully about this tend to land in different places. Some argue that bringing life into difficult circumstances is not inherently wrong, that the value of existence outweighs the constraints under which it occurs. Others argue that knowingly creating people who will spend their entire lives in confinement, serving a mission they never consented to, raises serious questions about autonomy and dignity that cannot be dismissed. There is no settled answer. And there is one more dimension that tends to emerge only when you think carefully about the specific destination we are discussing tonight. Imagine launching a generation ship in the year 2100 using the best technology available at that time. The ship travels for 300 years, arriving at Alpha Centauri in the year 2400. Now imagine that in the year 2200, 100 years after departure, a new propulsion technology is discovered that can reach Alpha Centauri in 20 years. The generation ship, still 200 years from its destination, would eventually be overtaken by vessels launched centuries after it departed. The descendants of the original crew would arrive to find that the civilization they left behind had been at Alpha Centauri for nearly 2 centuries already. Researchers sometimes call this the incessant obsolescence problem. It adds a melancholy dimension that resists easy resolution. Perhaps the most honest thing that can be said about generation ships is this: they represent the most extreme version of a very human trait, the willingness to begin a journey knowing you will not be the one to finish it, to plant a tree whose shade you will never sit under, to lay a foundation for a building whose upper floors will be built by hands not yet born. There is a particular kind of love in that, and a particular kind of grief. Humanity has done it before, in smaller ways. Cathedrals that took centuries to build, long-term scientific projects designed to span multiple generations of researchers, the slow accumulation of knowledge across millennia that eventually produces the moment when someone can look up at a star and know its distance to 4 decimal places. A generation ship would be the longest and most literal version of that impulse our species has ever attempted. The longest relay race imaginable, with a baton passed not between runners on a track, but between parents and children. In the darkness between stars, the star does not care how long it takes to arrive. It will keep burning regardless. Whether that patience is an invitation or simply a fact of physics depends, perhaps, on what kind of universe you believe you are living in. For now, let us leave the generation ship to its long, slow journey and turn our attention to a different set of questions. Because while philosophers debate the ethics of sending communities to the stars, engineers have been asking something more immediate. What if we do not need to go slowly? What if the propulsion problem is not as immovable as it first appears? What if we could go faster? There is a particular satisfaction in watching a problem that seems immovable begin, slowly and with great effort, to move. The rocket equation imposes severe constraints on chemical rockets. The energy stored in burning propellants is simply not dense enough to overcome the compounding mass requirements of high-speed interstellar travel. That is not an engineering failure. It is a fact about chemistry. And facts about chemistry cannot be argued with, or outspent, or engineered around. They can only be replaced by a different category of physics entirely. That replacement is what this chapter is about. Let us begin with the quietest revolution in spacecraft propulsion, one most people have never heard of, despite the fact that it has already flown in space and proven its principles in the most demanding test environment imaginable. Ion propulsion. The concept is elegantly simple. Instead of burning a chemical fuel, an ion engine ionizes a propellant, typically a noble gas like xenon, stripping electrons from atoms to create electrically charged particles. Powerful electric fields then accelerate those charged particles to very high speeds before ejecting them out the back of the spacecraft. The ejection creates thrust by the same basic reaction principle as any rocket. The difference is in exhaust velocity. A chemical rocket ejects its exhaust at speeds of roughly 2 to 4 kilometers per second. An ion engine ejects its exhaust at speeds of 20 to 50 kilometers per second. And in some designs even faster. That higher exhaust velocity means the engine extracts far more thrust from each kilogram of propellant. Ion engines are extraordinarily efficient. The catch is thrust. Ion engines produce very small amounts of force. The Dawn spacecraft, which used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres, produced a maximum thrust of about 90 millinewtons. Do you want to know what 90 millinewtons feels like? It is roughly the force you would feel if you placed a single AA battery in the palm of your hand. A single battery's weight of force. Dawn's ion engine was not going to accelerate anyone to Alpha Centauri quickly, but it ran continuously for years, accumulating velocity in a way that chemical rockets, which burn briefly and then coast, cannot match. Over the course of its mission, Dawn changed its velocity by more than 11 kilometers per second using only about 425 kilograms of xenon propellant. A chemical rocket achieving the same change would have required enormously more propellant mass. Ion propulsion represents a genuine philosophical departure from chemical rocketry. It demonstrates there are other ways to generate thrust, and that efficiency matters enormously when distances are measured in light years. For interstellar travel, ion propulsion in its current form is still far too slow, but the direction it points is real and important. The next step up in energy density takes us into nuclear physics. Nuclear thermal propulsion works by using a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures, then exhausting that superheated propellant through a nozzle to generate thrust. The energy comes from nuclear fission rather than combustion. Because a nuclear reactor can heat propellant to far higher temperatures than any chemical process, nuclear thermal rockets achieve exhaust velocities roughly twice those of the best chemical engines. Nuclear thermal propulsion is not hypothetical. The United States developed and ground-tested nuclear thermal rocket engines in the 1960s and early 1970s under a program called NERVA, which stood for Nuclear Engine for Rocket Vehicle Application. The NERVA engines demonstrated sustained operation and confirmed the basic principle. They were never flown in space, largely due to shifting political priorities following the end of the Apollo program's ambitions. But the engineering was real. The results were documented. The tests happened. Journey times to Alpha Centauri would still be measured in tens of thousands of years at nuclear thermal speeds. But the efficiency gains are genuine and meaningful. For interstellar travel, nuclear thermal is a step in the right direction, not a large enough step. To make a larger step, you need a fundamentally more powerful nuclear process. This brings us to one of the most audacious engineering proposals in the history of spaceflight. A concept so bold, so strange in its details, and yet so grounded in real physics that it is difficult to dismiss even when you have read everything about it. Project Orion. In the late 1950s, and through much of the 1960s, a group of serious and brilliant physicists and engineers working at General Atomics in San Diego developed a detailed proposal for a spacecraft propelled by nuclear explosions, not nuclear reactors, not nuclear thermal heating. Nuclear bombs. The concept worked like this. A large spacecraft would carry a supply of small nuclear devices. These devices would be ejected from the rear of the spacecraft at regular intervals and detonated at a specific distance behind it. The explosion would produce a rapidly expanding wave of plasma. That plasma would strike a large pusher plate mounted at the rear, transferring momentum to the vehicle and accelerating it forward. A system of shock absorbers between the pusher plate and the crew compartment would smooth the impulses into something resembling continuous acceleration. The physics worked. The team behind Project Orion included Freeman Dyson, one of the most creative theoretical physicists of the 20th century, who later described his time on the project as among the most intellectually exciting of his career. Dyson and his colleagues calculated that an Orion spacecraft could, in principle, reach speeds of several % of the speed of light. For larger versions, using thermonuclear devices rather than fission bombs, speeds approaching 10% of the speed of light were considered achievable by the physics. If not immediately, by the engineering. A journey to Alpha Centauri at 10% of the speed of light would take approximately 43 years. 43 years. A single human lifetime, or close to it. The practical obstacles were, and remain, severe. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear detonations in space, effectively ending the project's development. The radiation released by thousands of nuclear detonations in near-Earth space, and the consequences of any launch failure carrying that payload, make Project Orion in its original form essentially impossible to pursue in the near term. But the physics remains valid. Variations on the concept, including proposals for using nuclear pulse propulsion only after the spacecraft has been launched to a safe distance from Earth by conventional means, have been discussed in serious technical literature. Project Longshot, a study conducted by NASA and the United States Naval Academy in the late 1980s, proposed an unmanned interstellar probe using nuclear pulse propulsion that could theoretically reach Alpha Centauri in approximately 100 years. 100 years. Still longer than a human lifetime, but shorter than the thousands of years required by chemical propulsion. The direction of progress is real. There is one more nuclear propulsion concept worth placing here. Nuclear fusion propulsion would use the same process that powers the Sun itself. The fusion of light atomic nuclei releases energy far more efficiently than fission. A fusion rocket, if it could be built, would have exhaust velocities and efficiency figures that dwarf even the most optimistic nuclear fission designs. The problem is that controlled nuclear fusion, the kind sustained in a laboratory rather than detonated in a bomb, has been the subject of intensive research for more than 60 years and has not yet been achieved in a practically useful form. As of December of 2022, the National Ignition Facility in California achieved fusion ignition for the first time, a genuine historical milestone. But the gap between achieving ignition in a laboratory and building a sustained fusion reactor small enough and reliable enough to power a spacecraft remains large. The field is moving. The underlying physics is real. But the timeline is uncertain in ways that make confident predictions unwise. What we can say is this: the arc of nuclear propulsion concepts, from nuclear thermal to nuclear pulse to nuclear fusion, represents a genuine progression toward the speeds required for practical interstellar travel. Each step requires solving harder problems, But each step moves us meaningfully closer to a regime where decades replaces millennia in our estimates of journey time. All of the technologies we have discussed so far share one fundamental characteristic. They carry their energy source with them. The propellant, the fuel, the bombs, whatever form the energy takes, must all be loaded onto the spacecraft at the beginning of the journey. And, as the rocket equation established, every kilogram of energy source added to the spacecraft adds to the mass that must be accelerated, which requires more energy source, which adds more mass. What if the energy source did not have to be carried at all? What if the spacecraft could be pushed by energy supplied from somewhere else, from behind, rather than from within? That question leads directly to one of the most remarkable scientific proposals of the early 21st century. A project backed by some of the most recognizable names in science and technology, designed to send the first human-made object to another star system within a human generation. Its name is Breakthrough Starshot, and it is where we are going next. On April 12 of 2016, at a press conference in New York City, a group of remarkable people stood together and announced something that would have sounded like pure science fiction from any previous era of human history. They were going to send a spacecraft to Alpha Centauri, not in centuries, not in thousands of years, in approximately 20 years of travel time. The people making this announcement were not dreamers at the fringe of the scientific community. They included Yuri Milner, a Russian-born technology investor who had already funded some of the most ambitious scientific initiatives of the modern era through his Breakthrough Initiatives program. They included the late Stephen Hawking, arguably the most recognized theoretical physicist of the late 20th and early 21st centuries, who appeared via video link and lent the announcement the weight of his reputation for clear-eyed engagement with what physics actually allows. And they included Pete Worden, former director of NASA's Ames Research Center, who brought decades of institutional aerospace experience to the proposal. The initiative was called Breakthrough Starshot. Before we go any further, let us be clear about what this actually is. Breakthrough Starshot is a serious, funded research and development program. It is not a completed technology. No spacecraft has been built. No laser array exists. What exists is substantial scientific engagement, published research across multiple institutions, and $100 million committed by Milner to the research phase when the project was announced. The goal is to determine whether the engineering challenges can be solved, and to begin solving them. That distinction matters, and the project's own scientists have been admirably clear about it. With that honesty established, let us look at what they are proposing. The core idea behind Breakthrough Starshot is elegant in the way that genuinely creative solutions tend to be. It does not try to solve the rocket equation by finding a better fuel. It removes the fuel from the equation entirely. Here is how it works. The spacecraft, which the project calls a starship, would be extraordinarily small. The target mass for each starship is approximately 1 gram, the mass of a small paperclip. At that mass, even the rocket equation's tyranny becomes manageable. Accelerating 1 gram to a significant fraction of the speed of light requires far less energy than accelerating a conventional spacecraft. The energy requirement is still large, but it is large in a way that existing or near-future technology might actually supply. The propulsion would come not from any engine aboard the starship itself, but from a powerful array of lasers on Earth. The starship would be attached to a lightsail, a thin reflective membrane, perhaps a few meters across, but only a few hundred atoms thick. The laser array would focus its combined energy onto that sail. Light carries momentum. When photons from the laser strike the reflective sail and bounce back, they transfer a tiny amount of momentum to the sail. With enough photons, enough laser power, focused precisely enough on a small enough sail, the accumulated momentum can accelerate the craft to extraordinary speeds. The target speed is 20% of the speed of light. At that velocity, the journey to Alpha Centauri would take approximately 20 years. The numbers that make this possible are striking. The project envisions a laser array with a total power output of approximately 100 gigawatts, focused on the sail for roughly 10 minutes during the acceleration phase. 100 gigawatts is roughly equivalent to the total output of 100 large nuclear power plants, all focused simultaneously on an object the size of a postage stamp. The acceleration the starship would experience during those 10 minutes would be roughly 10,000 times the force of Earth's gravity. No human being could survive it, but a chip and a sail, properly designed to withstand those forces, might. After those 10 minutes of acceleration, the starship would be traveling at 20% of the speed of light. The laser would no longer be able to keep up with it. From that point, the craft would coast, completely unpowered, across the void for approximately 20 years, collecting data as it went and, in the final approach, transmitting what it found back toward Earth. The data transmission home, traveling at the speed of light, would take 4.37 years to arrive. So, approximately 24 years after launch, Earth would receive its first close-up measurements from another star system. The underlying physics is sound. The project has attracted serious scientific engagement from researchers at Harvard, Cambridge, UC Berkeley, and other institutions. The direction is real, but the challenges are profound, and the project's own researchers have been honest about them. The laser array is the first and most immediately daunting challenge. 100 gigawatts of laser power, focused coherently on a point kilometers away, would require an array of individual lasers working in perfect coordination. The phase coherence required, the precise synchronization so that beams add together constructively rather than cancelling each other or heating the surrounding atmosphere, is an engineering problem of extraordinary difficulty. Nothing close to this scale has been built. The sail presents its own difficulties. It needs to be thin enough to have the right mass, reflective enough to convert laser energy into momentum efficiently, and it needs to survive the energy density of 100 gigawatts focused on a few square meters for 10 minutes without vaporizing. Materials that can do all three simultaneously do not currently exist, though research into advanced metamaterials and coatings is ongoing. The starship itself must survive not just the acceleration, but 20 years of travel through interstellar space. The radiation environment is harsh. The chip must carry scientific instruments, a power source, and a communication system capable of transmitting data across 4 light years, all in a package weighing approximately 1 gram. The miniaturization required is beyond current technology, though the trajectory of progress in microelectronics suggests it may not be beyond technology of the coming decades. The communication problem deserves particular attention because no amount of engineering fully eliminates it. The starship, traveling at 20% of the speed of light, will be moving away from Earth throughout the journey. Its transmitter, powered by a tiny onboard energy source, will need to send a signal across up to 4 light-years of space with enough strength to be detected by receivers on Earth. The inverse square law, which describes how signal intensity decreases with the square of the distance it travels, means even a small weakening over 4 light-years becomes a very significant challenge. The project has proposed using a small laser on the star chip to transmit data back rather than a radio antenna, since lasers can maintain beam coherence over longer distances. But even so, the received signal would be extraordinarily faint, requiring a large, precisely aimed telescope on Earth to detect it. There is one more thing about Breakthrough Starshot worth sitting with before we move on. The star chips, if they fly and survive the journey and successfully transmit their data back, will arrive at Alpha Centauri with no ability to slow down. At 20% of the speed of light, they have no braking mechanism. They will flash through the Alpha Centauri system in a matter of hours, photographing and measuring as fast as their instruments allow, and then continue outward into the deeper galaxy. A 20-year journey for a few hours of observation, and then the data, traveling back at the speed of light for another 4 years. There is something both thrilling and quietly humbling about that image. The most ambitious interstellar mission in human history, reduced to a fleeting glimpse, a postcard from the nearest star, written in the seconds of closest approach and taking years to arrive, like a letter sent across an ocean that takes months to reach its destination and can never receive a reply in the same season. But the underlying physics is sound, and the timeline, if the engineering challenges yield to sustained effort over the coming decades, places the first interstellar probe within the reach of people currently alive. The star, as always, is patient. Now, there is one more obstacle that must be understood before we move further. An obstacle that sits not in the engineering of the spacecraft, but in the space itself, in the thin medium through which any interstellar traveler must pass. It is quieter than an explosion, more diffuse than a wall, and at interstellar speeds, it is more dangerous than almost anything else we have discussed. The space between the stars is not empty, and what fills it has teeth. There is a common image of deep space that most people carry without examining it too carefully. Empty, black, silent, vast, but above all, empty. The word itself implies a kind of absence, a region where the concerns and hazards of the physical world have dissolved into pure nothingness. When we imagine a spacecraft moving between stars, we tend to picture it traveling through something like a perfect vacuum, a frictionless, featureless void where the only challenge is the sheer scale of the distance to be crossed. That image is not wrong. Exactly. Space is extraordinarily empty by the standards of anything we encounter on Earth. A cubic meter of air at sea level contains approximately 10 to the power of 25 molecules. A cubic meter of the best vacuum achievable in a laboratory might contain a few thousand molecules. A cubic meter of interstellar space contains, on average, roughly 1 atom. 1 atom per cubic meter. That is emptiness on a scale genuinely difficult to conceive. If you took every molecule out of the air in a room and replaced it with interstellar space, you would have something billions of times more empty than the finest vacuum any human machine has ever produced. And yet, that single atom per cubic meter becomes something very different when you are moving through it at a significant fraction of the speed of light. This is the insight at the heart of one of the most underappreciated challenges in interstellar travel, the interstellar medium, as astronomers call it. The thin mixture of gas and dust filling the space between stars is not simply an inconvenience at high speeds. At the velocities required to reach Alpha Centauri in a human lifetime, it becomes a hazard of a quite serious kind. Let us think carefully about what happens when a spacecraft moving at 20% of the speed of light encounters a particle of matter. At 20% of the speed of light, the spacecraft is traveling at approximately 60,000 kilometers per second. In the reference frame of the spacecraft, a particle sitting stationary in interstellar space is effectively moving toward it at that same speed. The kinetic energy of an object depends on its mass and the square of its velocity. When velocity is very large, kinetic energy grows very rapidly. A single hydrogen atom, the most common particle in the interstellar medium, carries kinetic energy at that speed roughly equivalent to a high-energy gamma-ray photon when it strikes the leading surface of the craft. One atom, and the craft sweeps through a column of interstellar space, 60,000 kilometers long every single second. Given the average density of interstellar hydrogen, the cumulative effect on spacecraft materials over years of travel at those speeds is a continuous erosive bombardment, slowly wearing away surfaces through a process called sputtering. Over 20 years, without pause. But hydrogen atoms, however numerous, are only the most abundant component of the interstellar medium. The medium also contains helium, heavier elements in trace quantities, and most importantly, for our purposes, dust grain. Interstellar dust grains are tiny particles of solid material, typically silicates or carbonaceous compounds, ranging in size from a few nanometers to perhaps a few tenths of a micrometer for the larger common grains. They are extraordinarily sparse. In most regions of the interstellar medium, you might encounter roughly 1 dust grain per cubic kilometer or less. 1 dust grain per cubic kilometer. At the speeds achieved by Voyager 1 or the Parker Solar Probe, and interstellar dust grain is a trivial hazard. The kinetic energy in any collision is small enough that well-designed spacecraft materials handle it without difficulty. Now ask yourself what changes when the speed changes. At 20% of the speed of light, a dust grain, the size of a period at the end of a sentence, perhaps 100 micrometers across, carries kinetic energy roughly comparable to a small explosive charge. A period at the end of a sentence, moving at 1/5 of the speed of light. It would punch through conventional spacecraft materials with violence entirely disproportionate to its barely visible size. The physics of hypervelocity impacts at those speeds has been studied carefully, primarily in the context of designing spacecraft to survive micrometeorite impacts in Earth orbit. Extrapolated to interstellar speeds, the numbers become significantly more alarming. The Breakthrough Starshot team has examined this problem and concluded it is manageable for a gram-scale chip, primarily because the small cross-sectional area of the star chip reduces the probability of a direct hit during the 20-year journey. Statistical calculations suggest a well-designed chip might survive intact, but for a larger spacecraft capable of carrying human beings, the cross-sectional area is enormously greater. The probability of a damaging dust grain impact scales with that area. Over 20 years, a human-crewed spacecraft traveling at high interstellar speeds would almost certainly encounter multiple impacts capable of causing serious damage unless armored in ways that add significant mass and feed back into the rocket equation. Various solutions have been proposed. A cloud of plasma surrounding the spacecraft could deflect charged particles. A sacrificial shield of material on the leading edge could absorb impacts before they reached the crew compartment. Some proposals suggest a swarm of smaller craft flying ahead to detect or clear hazardous particles. Each solution carries its own mass, its own complexity, its own potential failure modes. None represents a simple fix. Now let us turn to the radiation dimension, which exists even in perfectly empty space with no particles at all. Galactic cosmic rays permeate the galaxy. They arrive from all directions, continuously, without pause, accelerated to enormous energies by supernovae, pulsar wind nebulae, and other violent astronomical events throughout the Milky Way. Unlike interstellar medium particles, cosmic rays cannot be avoided by careful routing or deflected by sacrificial shielding alone. They pass through ordinary matter with relative ease. And denser shielding creates a secondary problem. It generates a shower of secondary particles as the cosmic ray interacts with the shield material. Those secondary particles are themselves harmful to crew members deeper inside the spacecraft. This secondary particle problem means that simply adding more shielding does not linearly reduce the radiation dose. At some thickness, adding more material can actually increase the effective dose received by the crew. The optimization of shielding against cosmic rays is a genuine and difficult engineering challenge, with no perfect solution using currently known materials. There is one more radiation source that becomes relevant at high interstellar speeds. One unique to relativistic travel. At 20% of the speed of light, the spacecraft is moving into the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates the entire universe, compressing its wavelength and increasing its energy through the Doppler effect. At 20% of light speed, this effect is modest. But at higher fractions of the speed of light, the blue-shifted cosmic microwave background eventually becomes a meaningful radiation source in itself, requiring additional forward shielding that adds mass to the craft. The space between the stars is, in summary, not empty in any sense. A spacecraft traveling at high speed can afford to treat it as such. It is thin, sparse by every terrestrial measure, but it is present, and at interstellar velocities, presence is enough. There is something almost philosophical about this particular obstacle. The vast emptiness separating us from Alpha Centauri is precisely what makes the journey possible in one sense. No planets to navigate around, no atmospheric drag, no competing gravitational fields demanding constant correction. And yet, that same emptiness is not emptiness at all. It is a medium with texture and content, and the capacity to damage what passes through it at sufficient speed. The universe offers no free passages. Every route has its toll. Understanding the toll is not the same as accepting defeat. It is the same as planning accurately. And accurate planning is the only kind that has ever actually gotten anyone anywhere. We have now surveyed the obstacles with some thoroughness. The distance, the propulsion constraints, the biological limits of the human body, the challenges of sustaining communities across generations, the exotic and ambitious engineering of nuclear pulse drives and lightsails, the thinly spread but real hazards of the medium through which any traveler must pass. What we have not yet discussed is the destination itself, because the journey to Alpha Centauri is not just a story about getting there. It is also a story about what is actually there when you arrive, about what we have learned in recent years, about the worlds that may be waiting at the end of that long, dark road. And what we have found is surprising in ways that are both hopeful and quietly sobering in equal measure. For most of human history, the question of what might exist around the nearest stars was purely philosophical. We could observe the stars themselves, measure their brightness, their spectra, their motion across the sky over decades of careful observation. We could infer their temperatures, their sizes, their compositions, their ages. But planets were a different matter entirely. A planet orbiting another star is a tiny, dim body next to a blazing stellar furnace. Like a moth hovering next to a searchlight, the reflected light of a planet is overwhelmed by the direct light of its parent star by factors of billions. For most of the history of astronomy, detecting such a signal was beyond any instrument available to science. That changed in the 1990s. A combination of new technologies and patient, precise observation began to reveal planets around other stars. The field of exoplanet research, which scarcely existed as a discipline before 1995, has since grown into one of the most productive and surprising areas in all of astronomy. As of the mid-2020s, astronomers have confirmed the existence of more than 5,500 exoplanets, with thousands more candidates awaiting confirmation. The methods used to find them are indirect but powerful. The radial velocity method detects the tiny wobble that a planet's gravity induces in its parent star, showing up as a rhythmic shift in the star's spectral lines. The transit method detects the slight dimming of a star's light as a planet passes in front of it, blocking a small fraction of the stellar disk. For the Alpha Centauri system, the hunt for planets has been particularly intense, precisely because its proximity makes it the most compelling nearby target in all of exoplanet science. And that hunt has produced results, real results, confirmed by multiple independent observations. The most significant involves Proxima Centauri. In August of 2016, astronomers from the European Southern Observatory announced the discovery of a planet orbiting Proxima Centauri. The announcement was the result of years of careful radial velocity measurements taken with the HARPS spectrograph at the La Silla Observatory in Chile, combined with additional data from other facilities. The planet, named Proxima Centauri b, was found to have a minimum mass of approximately 1.27 times the mass of Earth, making it a rocky terrestrial planet. And its orbital period of 11.2 days places it squarely within what astronomers call the habitable zone. The range of distances from a star at which liquid water could theoretically exist on a planet's surface given the right atmospheric conditions. A roughly Earth-sized planet, in the habitable zone, of the nearest star to our Sun. The excitement was real, and the caution turned out to be equally necessary. Because Proxima Centauri is not a gentle star, red dwarfs, like Proxima, are cooler and dimmer than our Sun. That is why a planet needs to orbit so close, completing a full orbit in just 11 days. to receive enough warmth for liquid water. And that proximity creates problems. The first problem is tidal locking. A planet orbiting so close to its star for billions of years will have its rotation gradually slowed by tidal forces until one side permanently faces the star and the other permanently faces away. A world with a permanent day side baking in constant stellar radiation and a permanent night side plunged into perpetual darkness. Whether such a world can maintain a stable, habitable climate is a serious question. Some climate models suggest atmospheric circulation could transport heat efficiently enough to maintain moderate temperatures across a broad band of the surface. Others are less optimistic. The answer depends on the specific composition and thickness of the atmosphere in ways we currently cannot measure from Earth. The second problem is more severe. Proxima Centauri is what astronomers call a flare star. It produces regular, powerful flares, sudden, intense bursts of ultraviolet radiation and X-rays that can be hundreds of times more energetic than the largest solar flares our own sun produces. In May of 2019, astronomers recorded one of the most powerful flares ever observed from Proxima Centauri. The event, detected across multiple observatories simultaneously, produced an ultraviolet brightening of the star by a factor of approximately 1,000 over the course of a few seconds. 1,000 times brighter in a few seconds. If Proxima Centauri b has an atmosphere, that atmosphere would absorb a significant portion of each flare's energy, partially shielding the surface. But each flare also carries the potential to erode that atmosphere over time, stripping away molecules from the upper layers through a process called atmospheric sputtering, similar to what happened to Mars, as it lost its magnetic field and its atmosphere was gradually worn away by the solar wind over billions of years. Whether Proxima Centauri b retains a substantial atmosphere after billions of years of bombardment by its parent star's flares is unknown. The James Webb Space Telescope, launched in December of 2021, has the capability to study the atmospheres of nearby exoplanets through transmission spectroscopy, detecting the chemical fingerprints of atmospheric gases as a planet passes in front of its star. Whether Proxima b is positioned to produce detectable transits as seen from Earth remains a matter of ongoing observation. There is a third concern about Proxima Centauri b that relates to something more fundamental than atmospheres or flares. The magnetic field, Earth's magnetic field, generated by the circulation of molten iron in our planet's outer core, serves as an invisible shield against the solar wind. Without that shield, the solar wind would gradually strip away our atmosphere and expose the surface to far higher radiation levels than currently reach the ground. Mars, which lost its magnetic field billions of years ago, stands as a cautionary example of what happens to a world without this protection. Whether Proxima Centauri b has a significant magnetic field depends on its internal composition, its rotation rate, and the nature of its interior dynamics. A tidally locked planet, rotating very slowly in absolute terms, might generate a weaker magnetic field than a rapidly rotating one. The relationship between rotation rate and magnetic field strength is complex and not fully understood even for the planets in our own solar system. The combination of intense stellar flares, potential atmospheric erosion, possible tidal locking, and uncertain magnetic protection paints a picture of Proxima Centauri b that is considerably more ambiguous than the initial excitement of its discovery suggested. This is not a reason for disappointment. It is a reason for intellectual honesty. The universe does not arrange itself for our convenience or our narrative preferences. A world in a habitable zone is a promising beginning, not a guaranteed destination. The habitable zone defines only the range of distances at which liquid water is thermodynamically possible given the right conditions. It says nothing about whether those conditions actually exist. What Proxima Centauri b represents, in the most accurate terms available, is the most compelling nearby candidate we have yet found. A world of the right size, in roughly the right place around the nearest star to our solar system, facing severe challenges from its parent star that may have rendered it inhospitable, or challenges that may have been weathered in ways our current models cannot yet predict, leaving a world more complex and surprising than anything we have so far imagined. We genuinely do not know, and that uncertainty, while it might feel unsatisfying when we want a clear answer, is actually one of the most important truths in this entire story, because it means the journey to Alpha Centauri is not just a journey to cover a known distance. It is a journey into genuine, irreducible uncertainty, a journey to answer questions that cannot be answered from here. The only way to know what waits at Alpha Centauri is to go. There is one more thing worth saying before we move on. While Proxima Centauri b has received the most attention, the hunt for planets around Alpha Centauri A and B, the two sun-like stars at the heart of the system, continues with increasing sensitivity and ambition. In 2012, a study using the HARPS spectrograph reported a possible planet orbiting Alpha Centauri b, designated Alpha Centauri BB. The finding was subsequently called into question. Later analyses suggested the signal might be an artifact of the data processing technique rather than a genuine planetary detection. The potential planet was effectively retracted, a sobering reminder that careful science, using excellent instruments, can still produce false positives at the very edge of detection sensitivity. As of the mid-2020s, no confirmed planet has been announced around either Alpha Centauri A or B, though the search remains active and the question remains open. The universe keeps its secrets with a patience that outlasts any single generation of searchers. But the searchers keep searching. The worlds around Alpha Centauri, whatever they are there. They have been there for billions of years before any human eye looked up and wondered, and they will be there still when we finally find a way to look more closely. What those worlds are like, we will only know by going. And the question of whether any shortcut exists through the physics, whether the universe offers any passage more elegant than the long, slow road of propulsion and decades and generations, leads us next into the most beautiful and most carefully examined ideas in all of theoretical physics. Ideas about shortcuts through space-time itself. There is a particular kind of loneliness that has no name in any language. Not the loneliness of being alone in a room, not the loneliness of feeling unseen, or of losing someone you love, or of standing in a crowd and feeling invisible. Those are real and deeply human forms of loneliness. But the loneliness we are about to describe is of a different order entirely. It is the loneliness of distance, so vast that the concept of reaching out to another person becomes, in the most literal, physical sense, a project measured in years. To understand it, we need to begin with something so familiar we rarely think about it: the speed of light. We have mentioned this number many times tonight, always in the context of how fast something might travel. But light speed has a second role in the story of interstellar travel, just as important as its role as a velocity limit. It is also the speed at which all information travels. Radio signals, laser transmissions, any form of electromagnetic communication, regardless of frequency or encoding, travels at exactly the speed of light. When you send a message across space, that message moves at 186,000 miles per second. No faster. Not ever. On Earth, this limit is effectively invisible. We have built an entire civilization on the assumption that communication is essentially instant. That the person you are speaking to, wherever they are on this planet, might as well be in the same room. Remove the constraint of Earth's surface. Move into space. And the speed of light stops being an invisible background fact and becomes a very present, very limiting reality. The moon is roughly 1.3 light seconds away. When Apollo astronauts spoke to Mission Control in Houston, there was a noticeable pause in every exchange. A question took 1.3 seconds to reach the moon. The answer took another 1.3 seconds to return. 2.6 seconds round trip. Enough to make conversation feel slightly procedural. Not crippling, but present. Mars, at its closest approach to Earth, is approximately 3 light minutes away. At its farthest, about 22 light minutes. A question sent to a crew on Mars would take between 3 and 22 minutes to arrive. The answer would take the same amount of time to return. Real-time conversation becomes impossible. The crew must make their own decisions. Because there is no time to consult Earth and wait for guidance when something goes wrong. And that is Mars, a neighbor within our own solar system. Alpha Centauri is 4.37 light-years away. A signal sent from a spacecraft at Alpha Centauri travels at the speed of light for 4 years and 4 months before it arrives at Earth. Then the response travels back for another 4 years and 4 months. One question, one answer, 8 years and 8 months to complete. Let that sit for a moment. Just sit with it. If a crew member aboard a spacecraft at Alpha Centauri experienced a medical emergency and sent a distress call to Earth, the message would arrive here 4 years and 4 months after it was sent. The doctors who received it would formulate a response and transmit it immediately. That response would arrive at Alpha Centauri 4 years and 4 months after it was sent. The crew member would have been waiting 8 years and 8 months for medical advice that was needed in hours. In practice, a crew with any serious intention of surviving at Alpha Centauri would carry comprehensive medical resources and at least one physician, precisely because real-time medical consultation with Earth would be impossible. But the medical scenario illustrates the deeper principle with particular clarity. Every interaction between the crew at Alpha Centauri and anyone on Earth is not a conversation. It is correspondence. Slow correspondence. The kind that unfolds over years and requires each party to write complete, self-contained messages, rather than the rapid back and forth between people who share the same present moment. And here is the dimension of this that cuts deepest. Human beings are social creatures in a very deep sense. Our nervous systems are calibrated for connection, the sound of a familiar voice, the knowledge that someone who loves you is reachable, the ability to ask for help and receive it within a reasonable time. These are not luxuries. They are part of the infrastructure of psychological health. Astronauts on the International Space Station can call their families, watch live television, participate in limited ways in the daily rhythms of Earth life. The isolation of an orbital mission is real and documented, but it is cushioned by the constant accessibility of home. The crew at Alpha Centauri would have none of that cushion. The people they left behind on Earth would age 4 years before a single message home was even received. By the time any response arrived back, nearly 9 years would have passed. Children left behind as infants would be approaching adolescence. Parents who were in good health at departure might be gone. And every message received from Earth would arrive as a message from the past. News that was 4 years old by the time it was read. The Earth they were communicating with was not the Earth that existed when the signal arrived. It was the Earth of 4 years ago, frozen in the amber of light-speed delay. This temporal displacement has no perfect analogy in human experience. It is something genuinely new. The letters that took months to cross oceans in the age of sail were slow. But sender and recipient still lived in the same flowing present moment. The gap was delay, not displacement. An interstellar crew would be in a different relationship with time itself. Earth's present would always be their future. Their present would always be Earth's past. There is also a practical dimension to the communication delay that has nothing to do with psychology and everything to do with mission design. Mission control, as the term is currently understood, cannot exist for an interstellar mission. Earth-based teams cannot intervene in real time. They cannot abort a maneuver, correct a navigation error, or respond to an emergency with any speed that matters. Every decision that needs to be made quickly must be made by the crew. Every contingency that can be anticipated must be planned for in advance. Every system must be designed to fail safely without external intervention. The crews of sailing ships in the age of exploration faced something similar. They were equally beyond real-time communication with any authority on land. They made their own decisions, faced their own emergencies. But those crews could stop. They could anchor. They could resupply from local sources. An interstellar crew cannot stop, cannot anchor in the void. The consequences of any decision error compound across years and decades without the possibility of rescue. The message problem is, in many ways, a quiet metaphor for the entire enterprise of reaching Alpha Centauri. It is not about the absence of a solution. Message can be sent. It is about the nature of the constraint, the hard, non-negotiable reality that some problems cannot be solved faster than physics allows. They can only be accepted, worked around, built into the design of things. There is a quiet wisdom in that, a reminder that maturity, whether in a person or a civilization, involves knowing the difference between the obstacles that yield to effort and the ones that simply have to be lived with. The speed of light is one of the latter. But here is the thing about constraints that cannot be overcome. They can sometimes be circumvented entirely, not by going faster than light, which physics forbids, but by finding a path that does not require traveling the full distance at all, because the equations of general relativity also describe something more exotic, something that, on paper at least, would allow a traveler to move from one point in space to another without crossing the distance in between. Not faster than light, but through a structure in space-time that connects two distant points, the way a tunnel connects two distant rooms. A wormhole. We are going there next. There are ideas in science that are both completely real in the mathematics and completely out of reach in the cosmos. Not because the mathematics is wrong, not because the physics is speculative, But because the gap between what the equations permit on paper and what the universe permits in practice is filled with requirements the cosmos does not currently seem willing to supply. The wormhole belongs to that category. Let us begin at the beginning. In 1915, Albert Einstein published his general theory of relativity, one of the greatest intellectual achievements in human history, where Newton had described gravity as a force acting between masses across empty space. Einstein described it as the curvature of space-time itself. Mass and energy curve the fabric of space-time. Objects moving through that curved space-time follow paths we experience as gravitational attraction. Shortly after Einstein published his theory, the physicist Karl Schwarzschild derived the first exact solution to the field equations, describing the space-time geometry around a perfectly spherical, non-rotating mass. This solution described what we now call a black hole, and what Schwarzschild's solution also implied, which Einstein and the physicist Nathan Rosen explored in a 1935 paper, was the existence of a mathematical structure within that geometry that connected it to another region of space-time entirely. If you solve the equations carefully, the geometry did not simply end at a singularity. It connected, through a kind of bridge, to another solution on the other side. This mathematical bridge became known as an Einstein-Rosen bridge. Later, the physicist John Wheeler gave it the name we use today, a wormhole. The concept is this: a tunnel through space-time connecting two distant points. A traveler entering one end would emerge from the other without having traversed the space between them. In principle, a wormhole could connect Earth to Alpha Centauri in a way that makes the 4.37 light-year distance irrelevant. A traveler entering one end might emerge near Alpha Centauri in hours or days. The underlying physics is real. The Einstein field equations genuinely permit solutions that describe wormhole-like structures. This is not a conjecture or an approximation. It is a direct consequence of the mathematics that has been tested and confirmed to extraordinary precision. From the GPS satellites navigating our daily lives to the detection of gravitational waves from merging black holes a billion light-years away. So, why are wormholes not the answer? The problem arrives in layers. The first layer is stability. The Einstein-Rosen bridges that appear in the mathematics are not stable structures. They collapse before any signal, let alone any material object, could pass through them. The timescale of their collapse is essentially instantaneous by any human measure. Can a wormhole be stabilized? Can the geometry be held open long enough for something to pass through? The mathematics says yes. In principle, a wormhole can theoretically be held open by threading it with a particular type of material that has a negative energy density. Not negative in the sense of debt, negative in the sense of energy that is less than the 0-point energy of the vacuum. Matter or energy with this property is called exotic matter, and it pushes against the geometry of space-time in a way that opposes the collapse of the wormhole throat. Exotic matter with negative energy density is not entirely fictional. Quantum mechanics permits a related phenomenon called the Casimir effect, in which the vacuum between two closely spaced conducting plates has a lower energy density than the surrounding vacuum, producing a small but measurable attractive force between the plates. This has been confirmed experimentally and represents a genuine quantum mechanical effect, but the Casimir effect operates at the scale of nanometers and produces energy differences so small they bear no relationship to the quantities required to stabilize a traversable wormhole of any useful size. No exotic matter with the required properties has ever been observed. No confirmed mechanism in any known physics exists for producing it in useful quantities. The physicist Kip Thorne, who shared the Nobel Prize in Physics in 2017 for his work on gravitational waves, and who has contributed some of the most important theoretical analyses of wormhole physics, has written honestly about the deep uncertainties involved. Traversable wormholes are consistent with general relativity, but general relativity is not the final word on physics. The quantum mechanical behavior of spacetime at the scales relevant to wormhole throats requires a theory of quantum gravity that does not yet exist. And when such a theory is eventually developed, it may close off the possibility of traversable wormholes entirely. There is a second layer of difficulty that operates independently of the exotic matter problem. Even if a traversable wormhole could be created and stabilized, the question of where its other end would be is not trivial. Creating a wormhole with one end here and the other end near Alpha Centauri would require either the ability to physically place one end there through conventional travel, which defeats the purpose, or some mechanism for selecting where the far end opens. No known physics describes such a mechanism. There is a third layer, stranger still. If a wormhole connected 2 points in space, and if the two ends were moving relative to each other, which they almost certainly would be, then relativistic time dilation means the two ends would not be synchronized in time. It might be possible to use such a wormhole not just as a shortcut through space, but as a shortcut through time itself. This possibility, which Kip Thorne and his collaborators explored in a landmark paper in 1988, raises deep questions about causality and the fundamental consistency of a universe that contained traversable wormholes. Many physicists believe the universe protects itself from such paradoxes through what Stephen Hawking called the chronology protection conjecture. But this conjecture remains unproven. So where does all of this leave the wormhole? It leaves it as something very specific, an idea that is mathematically consistent with our best current theory of gravity, an idea that would, if realizable, solve the distance problem in the most elegant way imaginable, and an idea that requires, for its realization, physics that does not currently exist, materials that have never been observed, and an understanding of quantum gravity that has eluded the best minds in physics for nearly a century. Not impossible. That is the honest statement. Nothing in current physics proves that wormholes are impossible. But the gap between their theoretical existence in the equations and their practical existence in the universe is filled with unanswered questions, each of which might, when answered, close the door a little further. There is a particular kind of beauty in a door the universe almost opens. The wormhole lives in the equations with the same quiet insistence as black holes and gravitational waves and the expansion of space, all of which were once considered purely theoretical, and all of which turned out to be real. It would be rash to say the universe will never offer us this passage, but it would be equally rash to plan a mission around it. The door is open. In the mathematics, whether it will ever open in the cosmos is a question this generation cannot answer. For now, we leave it where we found it. Beautiful, ajar in the equations, closed, for the moment. In practice, and we move to the next door. In 1993, a young Mexican physicist named Miguel Alcubierre was watching an episode of Star Trek. This is not, by the standards of theoretical physics, an unusual origin story. Science fiction has always had a complicated and productive relationship with real science. It inspires researchers. It gives names and shapes to concepts that formal mathematics describes only in symbols, and occasionally, it poses questions that turn out to be worth asking seriously. The question Star Trek posed to Alcubierre was this: could a spacecraft travel faster than light without violating the laws of physics? The conventional answer, taught in every introductory physics course, is no. Einstein's special theory of relativity establishes that nothing with mass can be accelerated to the speed of light. The speed of light is not just a very fast speed that happens to be difficult to exceed. It is a fundamental limit built into the structure of spacetime itself. But Alcubierre noticed something subtle in the way that limit is expressed mathematically. Special relativity prohibits objects from moving through spacetime faster than light. It says nothing about spacetime itself moving, and general relativity is full of examples of spacetime doing things that violate ordinary intuitions about speed. The expansion of the universe means that very distant galaxies are receding from us at speeds greater than the speed of light, not because they are moving through space faster than light, but because the space between us and them is expanding, carrying them away. This does not violate relativity because it is not motion through spacetime. It is the expansion of spacetime itself. Alcubierre asked whether the same principle could be applied in reverse. Could space expand behind a spacecraft and contract in front of it, effectively moving the spacecraft forward without the spacecraft itself accelerating through space at all? He worked out the mathematics, and the mathematics said yes. Alcubierre published his solution in a paper titled The Warp Drive Hyperfast Travel Within General Relativity in the journal Classical and Quantum Gravity in 1994. It described a spacetime geometry in which a region of flat spacetime, the bubble, sits within a framework of expanding space behind and contracting space in front. An object inside the bubble would be locally at rest, not accelerating, not experiencing any forces, simply sitting still while the bubble itself moved through space at any speed, including speeds greater than light, without violating relativity because the motion is in the space-time geometry rather than in the object's motion through it. Inside the bubble, no time dilation would occur relative to the outside universe. A journey to Alpha Centauri in a warp bubble, traveling at 10 times the speed of light, would take roughly 5 months. From the perspective of both the travelers and the people they left behind, the elegance is genuine. The mathematics are real. The solution satisfies Einstein's field equations without requiring any violation of special relativity. The response from the physics community was fascination tempered by careful scrutiny. The first problem was the same one we encountered with wormholes. The Alcubierre metric requires exotic matter with negative energy density to maintain its structure. Without exotic matter threading the bubble walls, the geometry collapses. And as we established, exotic matter with negative energy density in the required quantities has never been observed and has no known production mechanism. There is a second problem, distinct from the exotic matter issue, and in some ways more fundamental: causality. An Alcubierre bubble traveling faster than light would be, from the perspective of some reference frames, traveling backward in time. a network of warp-capable spacecraft, could in principle construct a path through spacetime that loops back to its own beginning. The paradoxes this introduces are treated as deeply serious problems in theoretical physics. There is a third problem that receives less attention but is arguably just as disqualifying for practical use. The interior of the warp bubble is causally disconnected from the bubble walls. What this means in practical terms is that the occupant of the bubble cannot control it from inside. The exotic matter arrangement that maintains the bubble's geometry is outside the bubble. Light from inside cannot reach the bubble walls during travel because the walls are moving away from any signal the occupant might send. The occupant is effectively a passenger in a vehicle they cannot steer, cannot stop, and cannot modify once it has started. How the bubble is created, how it is navigated, and how it is safely dissolved at arrival are all problems for which no solution exists within the current framework of warp drive physics. In 2012, physicist Harold White at NASA's Johnson Space Center published theoretical analyses suggesting that a modified warp bubble geometry might reduce the exotic matter requirements compared to the original Alcubierre design. White subsequently established a small experimental program called the Eagleworks Laboratory to explore whether any measurable spacetime effects could be produced in a laboratory setting. To be direct about what that program produced, no experiment has demonstrated a working warp field. No confirmed detection of spacetime curvature effects beyond measurement noise was reported. The theoretical basis for the proposed energy reduction has been questioned by subsequent analyses from other researchers. The scientific consensus remains that warp drive physics, while a legitimate area of theoretical inquiry, has not produced any experimental evidence and faces fundamental, unresolved obstacles. In 2021, a detailed analysis by physicists Alexei Bobrik and Gianni Martier proposed a more general framework for warp drive geometries, mapping out the space of possible solutions more systematically. Their work confirmed that all known warp drive solutions require exotic matter and that the fundamental obstacles remain unresolved. The field is not dead. It is small, seriously pursued by a limited number of researchers, and characterized by the intellectual honesty that distinguishes good theoretical physics. The people working on these problems know exactly how large the gap is between mathematical consistency and physical realizability. They are not claiming warp drives are imminent or even achievable. They are exploring whether the universe's equations contain pathways that might, over very long timescales, yield insights that change what is possible. That is a legitimate thing to do. What it is not, and what its most careful practitioners would be the first to acknowledge, is a solution to the problem of reaching Alpha Centauri on any timescale relevant to current human civilization. So, here we are. We have traveled through the full landscape of what physics offers, and what it withholds, for the journey to the nearest star. Every approach, from the ships we have actually built, to the nuclear engines we have tested, to the lightsails being seriously engineered, to the mathematical structures living in the equations of general relativity. And what we have found is this: the universe does not make the journey easy. It imposes costs that are real and large, and in some cases may never be fully overcome. The distance is genuine. The physics is honest. The equations do not lie. But here is what else we have found. Every constraint we have encountered is a defined constraint. Every wall is made of known materials. The rocket equation is mathematics. And, mathematics can be worked with. The biological challenges of long-duration spaceflight are being studied by real researchers, making real progress. The radiation environment is measurable and increasingly well understood. The exotic matter requirements of wormholes and warp drives are obstacles. But they are specific obstacles, not infinite ones. And Breakthrough Starshot is real. The underlying physics is sound. The engineering challenges are severe, but not obviously impossible. A gram-scale probe accelerated to 20% of the speed of light by a focused laser array is not science fiction. It is a serious proposal backed by serious funding and serious science. And within the coming decades, it may become the first human-made object to travel to another star. The journey to Alpha Centauri is not closed. It is hard. It is farther away than anything we have ever reached. It requires capabilities we do not yet have, and may not have for generations. But it is not closed. And that matters in a way that goes beyond the specific question of one nearby star. Let us go back to the beginning. When we started this journey tonight, the title promised something terrifying. The terrifying journey to Alpha Centauri. And if you have been listening carefully, you may have collected along the way a substantial inventory of things that could reasonably earn that word. The distances that defeat intuition, the rocket equation that compounds against every ambition, the radiation that passes through walls, the dust grains that become explosive charges at relativistic speeds, the decades of isolation, the generations of people born and dying in transit without ever choosing the mission they were born into, the wormhole door that stands open in the mathematics and closed in the cosmos, the warp drive that requires matter the universe may not contain. That is a serious list. Every item on it is real. But spend a little time with that list and something begins to shift. None of those things are the universe being hostile. None of them are evidence that the cosmos is conspiring to keep us earthbound. They are simply what physics looks like at the scale of interstellar space. They are the natural consequences of laws that govern how matter and energy and space-time behave. At every scale, from the quantum to the cosmological, the universe is not terrifying. It is large, and largeness, when you make your peace with it, is not the same thing as terror. Think about what we have actually learned tonight. We learned that the nearest star to our Sun is part of a triple system, 3 stars bound together by gravity, each one ancient beyond any human frame of reference. We learned that one of those stars has a planet, a rocky world in its habitable zone, imperfect and uncertain in its prospects, but genuinely there, genuinely detected by real instruments, operated by real scientists who spent years of their lives watching the light from a small red star for a signal smaller than a heartbeat. We learned that the distances involved, while vast by every measure relevant to human life, are not infinite. They are specific. They are measured. They are known to 4 decimal places. We learned that human beings have already sent objects beyond the edge of our solar system, that we have already built instruments powerful enough to detect planets around other stars, that a serious, funded, scientifically credible proposal exists for sending a probe to Alpha Centauri within the lifetimes of people currently alive. We learned that the biological challenges of long-duration spaceflight are being studied with increasing sophistication, that the underlying physics of nuclear propulsion represents genuine and measurable progress toward the speeds required, that the mathematics of general relativity contains geometric structures that would if physically realizable, make the journey trivial in duration. None of this is the picture of a universe fundamentally closed to exploration. It is the picture of a universe that is expensive to explore, that extracts enormous cost in time and energy and ingenuity from anyone who wants to cross the distances it contains, but governed, at every scale, by laws that can be understood. And laws that can be understood can, at least in principle, be worked with. There is a version of tonight's story that ends in despair. That concludes from all the evidence we have surveyed that Alpha Centauri is, in any practical sense, unreachable. That the dream of interstellar travel is a beautiful fantasy the physics will not support. That version is available. The evidence would support it if you choose to weight it that way. But there is another version the same evidence supports. A version in which the difficulty of the journey is not a verdict on its impossibility, but a measure of its magnitude. In which every constraint is also a research program. In which the fact that we know exactly what stands between us and Alpha Centauri is itself a form of progress. Because you cannot solve a problem you have not yet defined. The second version seems, to this careful and honest reading of the evidence, more accurate. Not because it is more comfortable. Comfort is not the standard by which we judge accuracy in science. But because the history of what human beings have actually done, when given enough time and sufficient motivation and the accumulated knowledge of generations, suggests that defined obstacles have a poor record of remaining permanent. The ocean was once the end of the world. Then it became a crossing. The atmosphere was once an absolute ceiling. Then it became a threshold. The surface of another world was once a destination so remote it existed only in imagination. Then it became a place where human footprints persist in the dust, undisturbed for more than 50 years, waiting in the low lunar gravity for whoever comes next. Alpha Centauri is further than any of those crossings. The crossing will be harder. It will take longer. It will require capabilities we do not yet have and ideas that have not yet been conceived. Some of those ideas may be conceived by people not yet born, working in fields not yet named, building on knowledge that does not yet exist. That is not a reason for despair. That is a description of how science has always worked. Many previous limits turned out to be temporary. Not all of them. The speed of light is not going anywhere, but enough of them, enough of the walls that once seemed permanent, have given way to sustained human effort that the pattern itself deserves to be taken seriously. The word terrifying, in the title of this journey, was chosen deliberately, not because the journey is actually terrifying, but because it is the word our instincts reach for when confronted with something so much larger than ourselves that ordinary categories fail. What that word is really standing in for, when you examine it carefully, is not fear. It is awe. Awe is the feeling you get when something is so much larger than you that your usual sense of scale becomes temporarily useless. When the ground reference disappears and you are left floating for a moment in the presence of something genuinely vast, it is uncomfortable. Briefly, it can feel like fear, because both involve a sudden awareness of your own smallness. But awe is not fear. Awe is what happens when fear meets wonder, and wonder wins. The journey to Alpha Centauri is not terrifying. It is awesome, in the original and full sense of that word, in the sense of inspiring awe, of being so much larger than us that the encounter with its true dimensions changes. quietly and permanently. How we understand where we are in things. You are a small, warm, briefly living creature on the surface of one small world, orbiting one ordinary star among hundreds of billions in one galaxy, among hundreds of billions of galaxies in a universe 13.8 billion years old. That could be terrifying. Read one way. It is the most extreme statement of human insignificance possible. Read another way. It is the most extraordinary thing about being alive. You are a small, warm, briefly living creature on the surface of one small world. And you know all of that. You have instruments that can detect the wobble of a star 4 light-years away. You have mathematics that describes the curvature of space-time. You have history enough to know that many previous limits were temporary. And you have, somewhere in the part of you that looked up at the night sky as a child and felt something that had no name, the beginning of the only question that has ever really mattered. What is out there? That question does not require a spacecraft to be meaningful. It only requires the willingness to ask it honestly, to sit with its full weight, to let the distance be as large as it actually is. Without flinching, you have done that tonight. Somewhere above you right now, the light is traveling, not metaphorically, not as a figure of speech. At this exact moment, photons that left Alpha Centauri 4 years and 4 months ago are completing their journey through the interstellar medium, entering the outer layers of Earth's atmosphere, and arriving at the surface of this planet. Some of them are passing through whatever is above you right now, whether that is a ceiling or a floor or the open night sky itself. The light does not know it has arrived. Photons do not have experiences. They simply travel, at the speed that light travels, until they interact with something and stop. But the fact of the arrival is real. The photons from Alpha Centauri are here, continuously, quietly, delivering the most recent information the nearest star has sent us. Information from 4 years ago, by the time it lands. Hold that thought gently. It means Alpha Centauri is not distant in an abstract or merely numerical sense. It is present in the most literal way that distance allows. Its light is here, in this room, or just above it. The star itself is somewhere in the sky right now, below the horizon, if you are in the northern hemisphere, above it, if you are south enough to see it. In either case, shining with the same steady brightness it has maintained since before the first human being looked up and wondered what those lights were. It has been there through everything. It was there when the first stone tools were shaped, when the first boats were pushed out onto rivers, when the first cities rose along the Tigris and the Nile and the Indus. It was there when navigators crossed the Pacific by reading the stars and the swells, when Galileo pointed his tube of lenses at the sky and the universe quietly became larger, when the Saturn V rose from the launch pad in Florida and human beings left this planet for the first time. It was there last night, and it will be there tomorrow night. The distance between us and Alpha Centauri has not changed tonight. It is the same 4.37 light-years it was when you first pressed play. The rocket equation is still in force. The exotic matter for the wormhole is still not available. The laser array for Breakthrough Starshot has not yet been built. But something may have changed in the way that distance feels. Not smaller. That would be dishonest. And this entire journey has been built on honesty. The distance is not smaller. It is exactly as large as it ever was. But perhaps it feels different now. The way a mountain looks different after you have studied its geology and its history and the names of its passes. Not smaller, not closer, known. Part of a story you can hold. That is what tonight has been about. Not the promise that we will reach Alpha Centauri soon. We will not. Not in anyone currently listening's lifetime. Almost certainly. Not a reassurance that the journey is easy or that the obstacles are trivial. They are not. We have spent many hours making sure of that. What tonight has been about is something quieter. The practice of looking at something immense and staying with it, of letting the distance be real, of following the physics wherever it leads, even when it leads to equations that close doors, and sitting with the honesty of what those equations say without letting that honesty become despair. Because here is what the physics also says. It says that the same universe that places Alpha Centauri 4.37 light-years away also placed it there rather than 4,000 light-years away. By the standards of interstellar distances, we are practically neighbors. The nearest star to our Sun, in any direction, happens to be just around the corner in cosmic terms. It says that the same laws of physics that impose the rocket equation also permit nuclear fusion, which our own Sun demonstrates works beautifully, and which human beings achieved ignition of in a laboratory for the first time in December of 2022. The same laws that make exotic matter seem impossibly remote also produced quantum field theory and a century of surprises about what matter is like at its deepest levels. And there is something honest to be said here. Before we go any further into poetry, we do not know what the next century of physics will bring. We do not know whether the doors that are currently closed will open or stay closed. The universe has surprised us before, many times, and in ways we did not anticipate. Whether it will surprise us in the direction of interstellar travel is a question that no honest person can answer with confidence in either direction. What we can say is that the universe has a way, not always and not on any schedule we control, of being more permissive than it first appears to those still learning its rules. It says something about us, about what the fact that we are asking these questions actually means. The universe does not require any of its contents to be curious. Stars burn without curiosity. Galaxies collide without asking what galaxies are. Black holes consume without caring what they consume. The physics operates indifferently and completely, with no observer required. And yet here, on this small, warm world around this ordinary star, something happened. A process of chemical complexity organized itself over billions of years into nervous systems capable of modeling the universe they existed in. Those nervous systems eventually became curious about their own origin. They built instruments to see farther than eyes could see, developed mathematics to describe relationships too subtle for intuition, accumulated and transmitted knowledge across generations until the total understanding available to the species dwarfed what any individual could hold. And then they looked up at a light in the southern sky and measured how far away it was, and sat with the answer. You are part of that process, not metaphorically, literally. The curiosity that brought you here tonight, the willingness to spend time in the company of large and difficult questions, is the same curiosity that drove every step of the chain from the first careful observation of the stars to the equations of general relativity to the Breakthrough Starshot proposal to this moment right now. You do not need to be a physicist or an engineer to participate in that chain. You participate simply by caring, by being willing to look at the distance and not look away, by letting the universe be as large as it actually is and finding that you are still here, still curious, still breathing. On the other side of that encounter, the star is still there. It was there before you were born. It will be there after. Its light is crossing the void right now, arriving at this planet with the patient reliability of a process that does not know it is being observed. 4 years and 4 months for each photon to make the journey. An unbroken stream of arrivals, stretching back further than human memory, continuing forward further than anyone can see. There is something in that image worth holding as you drift towards sleep. Not the scale of the distance, not the discouragement of the unsolved problems, the steadiness of it, the fact that the light keeps coming, that the star keeps burning, that the distance, for all its vastness, is measured, named, known to 4 decimal places by human beings who cared enough to look carefully and stay with what they found, whatever questions remain unanswered tonight. And there are many. That steadiness is not nothing. It is, in fact, something close to everything. The nearest star is 4.37 light-years away, and we know that. We know the names of the 3 stars in its system. We know their sizes and their temperatures and their ages. We know there is a planet around the smallest of them. We know the physics that would govern any attempt to reach it. We know what we have not yet solved and why. And we know the shape of what solving it would require. We are, in the most literal sense, a species that knows where its nearest neighbor is, and is working out, slowly and honestly, how to visit. That is not the ending of a story about terror. That is the beginning of a story about reach, about the slow, uncertain, enormously costly, deeply human process of extending what is possible into what was once only imaginable. It will not happen tonight. It will not happen soon. But the light from Alpha Centauri will keep arriving. And somewhere on this small, warm planet, in laboratories and universities, and the quiet, late-night thinking of people who cannot quite let go of the question, the work continues. The star is patient. The work is patient. And so, perhaps, are we. Let your breathing slow now. Let the questions settle without demanding answers tonight. Let the universe be large and honest and full of things not yet understood. You have sat with it all tonight, and you are still here. Still whole. Still warm. The star will be there in the morning, and so will you. Sleep well,